Uh, Welcome to one more video on linear integrated circuits. In this video we shall see a series of videos connected to the discussion on data converters. So in the first video of data converters we should study digital to analog converters, which is called as DAC very popularly, and we are seeing the part 1 of DAC. Okay, what is a simple data system? So all sensor signals which are used to sense any physical quantity are analog in nature, and all computations are done digitally to reduce the process time. So we're going to sense the signal. All these sensor signals are analog in nature, and these analog signals which are measured have to be computed. So since the computation has to be done very fast, so it will be converted to digital. And once we convert those into digital, we do a certain process. We need analog signal to control the physical quantity. And you can see now first we had the analog signal, we converted to digital, and then digital signal is again back converted to the analog signal to control the physical quantity. So we need to convert analog signal to digital and then digital signal back to the analog signal. So this is a process which is required in most of the data systems, where we are converting analog to digital and then back from digital to analog signal. Now let us see the binary number, which is having a stream of string of n bits. So b1, b2, b3 up to bn forms an n bit word, and let us assume that bit b1 is called the most significant bit, MSB. So since it is placed in the first position, so it is the most significant bit, and bit pn is the least significant bit, so which is called as LSB. And we define the digital input as so we know the values of depending on the position. This is having a position of 2 power the first position 2 power minus 1, b2 multiplied by 2 power minus 2. Likewise, the last position is bn to the power of minus n. So this is digital input corresponding to the binary positions. The lower limit is reached when all the bits are 0. So this digital input will have the lower limit of 0 when all b1 to bn are 0. The upper limit will be reached when all the bits are 1. So we will reach upper limit when b1, b2, b3 all are 1. So the lower limit is when all the bits are 0, and the upper limit will be reached when all the bits are 1. Let us see the DAC basics, that is digital to analog converter basics. A DAC accepts an n-bit input word b1, b2, b3 up to bn with functional binary value, which is di. So which was defined in the earlier case. So di is nothing but b1 2 to the power of minus 1 plus b2 to the power minus 2 likewise, and produces an analog output proportional to this di. So proportional to this di, we are going to get an analog voltage. So this di is a binary input. The produced output voltage is represented by K into V reference di. So this K into V reference can be written as VFSR multiplied by the di value. So this is what is di value, where K is a scale factor, V reference is a VREF is the reference voltage. This is Bk. So this can take any value. This K can take any value from 0 to 1 to n. This value can be either 0 or 1. So B1 can be either 1 or 0. So B2 can also be either 1 or 0 depending on the logic level that is corresponding to the input. And we have this VFSR, which is nothing but K times the V reference, is called as full scale range. So VFSR stands for, as you can see, this is F stands for full, S stands for scale, R stands for range. So VFSR stands for voltage of the full scale range. frequently used values of VFSR is 2.5 volts, 5 volts and 10 volts. So these are the full scale ranges that will be usually used in the practical cases. Again, we should see some more basics of the. Now, depending on the input bit pattern, V naught can assume 2 power n different values ranging from 0 to full scale value. So you can see now we have the minimum value as 0, the maximum value is called as uh, VFSV. Now this is full scale value. So full scale value is given by 1 minus 2 power minus n into VFSR. So this 1 minus of 2 power minus n comes from by representing all bits as 111. So now the contribution of the MSB to the output is VFSR divided by 2. So MSB will contribute half of the full scale range voltage, and the NMF and the LSB contribution is VFSR divided by 2 power n. This is called the resolution, simply the LSB. So 1 LSB is equal to VFSR divided by 2 to the power of n. So when does this MSB will come and when does this LSB will come is, as you can see in the previous example, suppose in this particular case, if you consider all the bits as 0, 0 except this is MSB. If only this bit is 1, if all of the bits are 0, so we're going to end up with B1 divided by 2. So B1, since B1 is 1, it is 1 by 2. This is 0, this is 0, everything is 0. So we end up with V naught as VFSR divided by 2. So that's what is the contribution by the MSB. So assume that all the bits are 0, only LSB is 1. So assume that this is a 8-bit DAC. So when it is 8-bit, now all the bits are 0 except this. Now this is 1. So we end up with FSR divided by 2 power minus n. So that is FSR divided by 2 power minus, so this will be this is 1 into 2 power minus 8. So how do we write that as? So we can write that as, now only one, the LSB is 1. If all of the bits are 0, we end up with VFSR, that is full scale range, multiplied by 2 power minus n. Otherwise FSR divided by 2 power n, meaning the contribution by the LSB is VFSR divided by 2 power n. So that's what is written here. So we have the MSB contribution as VFSR divided by 2 and the LSB contribution as VFSR divided by 2 power n. So whatever the number of bits are, the MSB will always contribute to the half of the full scale range voltage for the output voltage, whereas the LSB contribution will be keep on reducing as the value of n increases. So that's why we say that the resolution of the DAC will going to be very small voltage if the number of bits are more. VFSV, where VFSV stands for the full scale voltage, is always 1 LSB less than VFSR. So we know that this is VFSR. So 1 is the full voltage minus of 1 LSB. So that's why 1 minus LSB FS 1 minus, okay, this is FSV is actually 1 LSB shorter than FSR. So that's what is given here. The quantity dr, which is given by 20 log of 2 power n, is called as the dynamic range of the DAC. So there is a quantity by name dr which talks about the dynamic range. So this is given by 20 into log to the base 10 2 power n. This in terms of dBs. If the number of bits are more and more, then the dynamic range of the DAC is more and more. You can see now for a 12-bit DAC, the VFSR is 10 volt and its LSB is 2.44 millivolt. So we get LSB as VFSR divided by 2 power n. In this case 2 power n is 2 power 12. So now it is 10 volt divided by 2 power 10. So this comes out to be 2.44 millivolt. VFSP is actually 10 volt minus of 1 LSP, which happens to be 9.9976 volts. And the DR happens to be from 20 log of to the base 10 to power n, which is 72.25 dBs. Let us see the important relations that are used in the DAC. Full scale range, which is VFSR, is usually almost equal to VCC, and DAC output voltage V0 is given by VFSR into the binary values, that is B1 into 2 power minus 1, B2 2 power minus 2, up to Bn 2 power minus n. The DAC resolution is given by 1 LSB, which is nothing but 2 FSR divided by 2 power n. The full scale voltage is always given by 1 minus 2 power minus n into VFSR, that is 1 LSB less than the VFSR. So we have taken some examples. Number of bits are 3. Number of bits VCC. What is the resolution, that is 1 LSB. What the full scale voltage. So full scale range is always equal to VCC. Full scale voltage is 1 LSB less than VCC or VFSR. And we have taken some input voltage example, and we want to estimate what is the output voltage. So let us consider the first n is equal to 3 now. Number of bits are 3. So we have VCC as 5 volt. 1 LSB happens to be 5 divided by 2 power 3, which is 5 by 8, happens to be 625 millivolts. So VFSV, that is full scale voltage of this DAC having 3 bits and a VCC of 5 volts is VCC minus 1 LSB, which happens to be 4.375 volts. For an input combination of 0, 1, 0, 0 is MSB and 1 is the in-between term and 0 is LSB. So this ends up with the output voltage of 1.25 volts. So similarly, we are considering n of 8, VCC of 5 volts. The LSB happens to be 5 divided by 2 power 8, so which comes out to be 19.5 millivolts. The full scale voltage will be 5 minus 19.5, which happens to be 4.98 volts. So we have taken an input combination of this. So you can estimate what is the V0. Now V0 is, now what is the decimal equivalent of this multiplied by the resolution. So because what we want is, so VFSR we know, which is 5. So we can estimate this value, so which is the binary equivalent of, the decimal equivalent of this. So you can actually get the value of V0 by substituting the values of corresponding B's and taking the power of 2 correspondingly. Now this is 2 power minus, this is 2 power minus 8, this is 2 power minus 7. So likewise you can just keep on editing the value. This is the LSB portion. The next one, this is LSB. If you substitute that, you can estimate what is the value of this. So similarly, we have taken n is equal to 16. The VCC is 10 volts. The 1 LSB happens to be 152.58 microvolts. The full scale voltage, you can see it is 9.99, very close to 10 volts. And input combination, you can expect what is, you can estimate what is the V0. You can carefully observe here, as the number of bits increases, the resolution is increasing. And you can see the full scale voltage is close to the supply voltage. So as the number of bits increases, the full scale voltage is almost equal to the full scale range, that is VCC, and we're going to have a better resolution of a DAC. So let us see how does a 3-bit DAC output look like. So we have taken a V reference voltage and there are 3 bits considered here, that is B0, B1, B2, B3. So B1 is MSB, B3 is LSB, that's what is written here. So this is actually 3 now. So for when all the bits are 0, 0, we are supposed to get a 0 volt. When LSB is 1, so we're going to get a voltage of 1 by 8. When it is 0, 1, 0, we're going to get 2 by 8. It is 3 by 8, 4 by 8. You can see for every bit change, the output changes by 1 LSB. So that's why it is called as LSB. If there is a change in LSB, the output also changes by 1 LSB. So the difference of the heights of the output voltage from one bit to the next consecutive bit. It